A function assigns any object in the domain to another object in the range. Most functions are not one-to-one, meaning there could be multiple arrows going to the same object in the range. So the inverse is not necessarily a function. But by restricting the domain to have one-to-one correspondence with the range, inverse becomes a function. The exponential function is one-to-one, so its inverse is automatically a function. But many functions are not one-to-one, so we have to choose a branch so that the inverse becomes a function. Mathematicians in the past have already made that decision for us, so we just follow their convention. But of course, we can create an inverse function for a non-standard branch of the domain. So for example, we can take the branch of the tangent function that does not go through the origin and find its inverse function. So how do we actually find inverse functions? Let's first look at it from a computational perspective. This is the function that represents the standard normal distribution. And we frequently are interested in finding the area of the left tail under this curve. So we can create a new function that represents the area up to some x value. Formally, this new function is the integral of the original curve from -infinity to x. As useful as this new function is, we don't have a nice formula for this new function. So the French astronomer Christian Comte painstakingly computed the values of this function by hand, and we now call this the z-table. Since we have enough values of this function computed, we can just read the table backwards to find the inverse function, which is commonly done in an elementary statistics course. So from a computational standpoint, finding an inverse is not very hard. Then how about algebraic standpoint? Let's level down to something easier, like a cubic function. This function needs 3 branch cut, and each of these branches can be inverted computationally. But can we come up with the formula for each branch? Formula indeed does exist, and in fact, it is called the cubic formula. But it is incredibly complex, pun intended, just to find an algebraic formula for inverses of such a simple looking function. And we are lucky to even have a closed form formula in terms of elementary functions. And what I mean by elementary function here, for the context of this video, it means a function that can be constructed at a high school level. So taking a rational power, or taking a power to a variable, and taking logarithms, trig functions, and their inverses, and any combination of addition, subtraction, multiplication, division, and composition we can make from them. And f is an example of an elementary function. As for a non-example, integral of the bell curve is non-elementary, but it was useful enough to have a name, the error function. Most of the time, inverses of some of the simplest functions are not elementary, like this quintic, or each branch of x times e to the x. Inverses of these two functions have been well studied, so they have names. Other times, we could have a function whose inverses can be written as a closed form in terms of these existing functions. But most of the time, you're completely out of luck, and you might as well name them yourself. So algebraically finding inverse functions is extremely difficult if we are lucky, and outright impossible most of the time. Now, doing calculus on non-elementary functions is usually very hard. Sometimes it's easy, like the error function, which is defined to be an integral of an elementary function, so we can just easily integrate it by parts, since we know the derivative of it. Other times, your best solution is just inventing new functions and calling it the answer. Despite the difficulties we have with symbolic calculus on these non-elementary functions, it is fairly easy with inverse functions, and we can compute derivatives and integrals of inverse functions without knowing them at all. You probably have seen the derivative of inverse functions in your first calculus class, but the integral is less well known. In this video, we will talk about what these two geometrically mean, and how far we can push symbolic calculus with these two theorems. Derivative of exponential functions are exponential functions. And that's not too surprising, since as the function gets bigger, the slope gets steeper proportionally. But what came as a surprise to me my first calculus class almost 15 years ago was that the derivative of logarithm is purely algebraic. Then my teacher proved why using implicit differentiation, and I realized e to the x is actually hiding in there. Soon after, I learned that the derivative of other inverse functions are similar. In general, we can derive all of these using the inverse function theorem, and the technique is essentially same as the individual cases. If we let u be the f inverse of x, then x is f of u. Then we can take the derivative on both sides with respect to x. Then we can divide by f prime of u. Lastly, we substitute back what u is in terms of x to get what we wanted. So we can push some symbols around, but what does this actually mean? Suppose we have the graph of a one-to-one function. Then each point on the graph represents a relationship between an input x and its output f of x. And since the function is invertible, we can think of y as the input and x as the output, with the mapping f inverse. Now, slope at that point is f prime of x, which is infinitesimal rise over run. Now, do a quick head tilt, and think of y as the input. Then, the derivative of f inverse of y is run over rise at the same point. So the inverse function theorem is basically saying that the derivative of f and the derivative of f inverse are reciprocals of each other at the corresponding point. Now, how about integrals? Algebraic proof isn't that hard, and we will start with the same substitution. But this time, we will keep the differential du on the right side. Then, we can substitute the integrand and the differential. Now, we want to integrate this by parts. So we can let u be u, and dv be f prime of u du. So v is equal to f of u. So the integral is uv minus the integral of v du. And we will call the integral of little f the big F, varying up to some constant. And once we substitute back what u was in terms of x, then we are done. We went through a lot of symbol crunching, but what does it actually mean geometrically? Choose any 2 points a and b in the domain, then we can get f of a and f of b. Then, the integral of f from a to b is the green area, and the integral of f inverse from f of a to f of b is the red area. Now, once we add these two areas together, the region is a big rectangle minus the little rectangle. So the area is equal to fb times b minus fa times a. Now, if we want a formula for the indefinite integral of f inverse, we want to change the limits of the integration on the vertical axis so that it goes from some fixed alpha to the variable y. And we can rewrite the horizontal limits in terms of alpha and y. So once we make the substitution in the equality, the red expression is the same as the antiderivative of f inverse, which is equal to y times f inverse of y, minus the integral of f evaluated at the f inverse of y. And everything else that depends on the constant lower limit, we can lump it up into a constant. Now, if you take a look at integrals of various functions, you will notice that the integrals of these inverse functions are in the same form. And this was no coincidence after all. Now, can we try some symbolic calculus on a non-elementary inverse function? Area under e to the negative x squared is square root of pi. So when Gauss defined the error function, he set the lower limit as 0 in order to make it an odd function about the origin, and put a constant of 2 over root of pi in order to have the range go from -1 to 1. This normalization may be convenient in some context, but for the purpose of this video, it's just an annoyance, so I will define a new function urf, which is like erf but unnormalized. Now, can we do some calculus on the inverse erf function? We will need the derivative of erf, which is just e to the negative x squared, and the integral of erf, which you can find it using integration by parts. So the derivative of erf inverse is 1 over the derivative of erf inverse. And we can flip the negative power to the top as positive power. Now, as per the integral of erf inverse, this is x times erf inverse minus the integral of erf inverse. Notice how these two terms are equal and opposite. So we just have one term left over. So we have calculated the derivative and the integral of a fairly exotic function. Now, what is the use of all this? Unless you are someone like me who enjoys learning abstract knowledge for the sake of it, you probably need a practical reason to learn something. But I promise you that the calculus of inverse functions is part of your everyday life. If you're into gaming, you're at the mercy of some randomness, whether it's random spray pattern or some lucky critical hit. And now more than ever, game designers use randomness to milk as much money as possible from their customers. Random number generators are ubiquitous in computing, from blockchains to computer simulations. This is the Maxwell-Boltzmann distribution, which is the probability distribution that represents speed of classical ideal gas. Classical meaning non-relativistic and non-quantum. And the mu here is the mean speed of the distribution, which varies with respect to the temperature and the mass of the molecule. This is an example of a probability distribution that is typically not found in the standard library of most programming languages. You could find a specialized math library like SciPy, or a mathematics software like MATLAB or Mathematica to make a random number generator of this distribution. But just to prove a point, I wrote the program from scratch to generate a random sample of this distribution. And it is made with, as you guessed it, calculus of inverse functions. In my next video, we will talk about how to create a random number generator of any distribution.